Hi everyone, my name is Minh Tran. I'm here to present our work, Graph Convolutional Networks, for Event Causality Identification with rich document-level structures. This is the work by me and my professor, Nguyen. In this work, we study the task of document-level Event Causality Identification, or ECI. Briefly speaking, the ECI task seeks to predict causal relation between a pair of event mentions in a text. We observe that the existing model for ECI are very limited to intra-sentence setting, and they do not work well in the intersentence setting, because first, it will fail to cover cases where event mentions appear in different sentences. Even where event mentions appear in the same sentence, it is often beneficial to look for further information from the document. Let's look at the following example. For this example, the interested pair of event mentions involve the word damage and wreck appearing in the last sentence. A system that only considers sentence context might find it challenging to predict causal relation due to the long distance and the appearance of many irrelevant words between event mentions. However, if a system can leverage on document-level information and can relate the current pair of event mentions to a similar pair appearing in the first sentence, it can exploit the clear evidence of causal relation presented in the first sentence following the phrase damage due to the wreck. With this motivation in mind, we propose a novel, graph-based deep learning model for document-level identity causal identification. We name our model DECI. Our model tries to construct an interaction graph to capture relevant mentions and connections between them in a document. Several information sources are incorporated in this interaction graph. We will discuss the information source in detail later. The generated interaction graph and the contextualized representations are then fed into a graph convolutional network to learn document-aware contextualized representations. These new representations are better for document-level causal prediction tasks. Our DECI consists of three main components. The first component is document encoder. This employs a transformer-based retrained language model to encode words into contextualized representations. The second component is graph generation and encoder, which is our main contribution. This component consists of two parts: generating interaction graph and encoding information from the interaction graph to contextualized representations to induce better representations for document-level causality prediction tasks. The third component is representation regularization, which is also an important part in our model. This component helps reducing noise in the generated interaction graph and helps improving the representations. Next, we will discuss each component in more detail. For the document encoder component, we employ the standard word model to encode words into contextualized representations. Any transformer-based retrained model can be used to handle a long document with words. We divide the document into segments of 412 word pieces to be encoded separately. Our next component is graph generation and encoder. The first part of this component aims to generate an interaction graph. which is represented by a list of nodes and an adjacency matrix. The list of nodes consists of all context words, all event mentions, and all entity mentioned in a document. The adjacency matrix encodes a connection between nodes. Its a connection between two nodes I and j is expressed by an interaction score, aij. Three groups of informations are exploited to estimate the interaction scores, including discourse-based, syntax-based, and semantic information. Next, we will go into further detail about the information source. The first group is discourse-based information, which tries to encode the surface connection of event and entity mentioned in the document. In this group, we express the interaction score, aij, in binary. It is equal to 1 if there is a connection, and it is equal to 0 otherwise. This group consists of three main information sources: sentence boundary, coreference structure, and mention span. The sentence boundary encodes the connection of two mentions appearing in the same sentence. Next, the coreference structure encodes the connection of event and entity mentions across the sentences. Here we employ the Stanford Core NLP toolkit to find the coreference mentions. The third information source is mention span, which tries to encode the connection between context words and mentions in a document. The second group is syntax-based information, which tries to encode the syntactic information. In particular, we employ the syntactic information from the sources dependency paths between mentions in the sentences. That is the interaction score, aij, is equal to 1 if two nodes I and j are neighbors in the sources dependency path. The third and the final group is semantic-based information, which tries to encode semantic similarity between nodes. This group consists of two information sources: context-based semantics and knowledge-based semantics. Both kinds of semantics are measured in real values instead of binary values as before. The context-based semantics measure the semantic similarity by taking the product of contextualized representation of nodes. On the other hand, the knowledge-based semantics measure the semantic similarity between nodes based on the external knowledge from the knowledge bases. Our work employs the WorkNet knowledge base, and the interaction score is measured by the link similarity score. After collecting all the interaction scores from the 6 information sources, we concatenate them into a vector, and then taking a product of it with a learnable weight vector Q. The final resulting interaction score is normalized across its rows to keep it in a general range. We use this adjacency matrix and the contextualized representations as input for the graph convolutional network. In this way, two nodes I and j directly interact and improve the representation learning from one another, even they are sequentially far away from each other in the document. The resulting document-aware contextualized representation are much better for document-level causality prediction tasks. In this work, we also introduce the representation regularization to help reducing noise and promote important edges in the generated interaction graph. Intuitively, the generated graph is typically dense and might consist of many noisy unnecessary edges. We hope to obtain a sparser graph by removing noisy edges which have the interaction score less than a threshold. We then seek to minimize the difference between the representations induced by both graphs. In our application study, we found out that this component is an important one to achieve competitive performance. In the experiment section, we perform 3 kinds of evaluations. We first evaluate our models for both intra and intersentence document level ECI on 2 benchmark datasets, Event Storyline and Causal Time Bank. We perform an application study to analyze the contribution of every model component and every information source that are integrated into the interaction graph. In addition, we perform cross-topic transferring evaluation on the Event Storyline dataset to show an additional benefit of the proposed model. For this evaluation, we train our model on data from source topic and evaluate the model on the target topic that has either low, medium, and high similarity with the source topic. Here are some important observations. Firstly, in comparison to the baselines and prior models, our proposed model significantly outperforms all of them for both intra and intersentence settings on both Event Storyline and Causal Time Bank datasets. Capturing context beyond sentences is clearly helpful even for intra-sentence causal prediction. Secondly, we observe that symbol burst implementations perform much worse than the model that incorporate document-level information into representations, such as LR+, LIP, and our proposed model. This shows that we actually need some mechanism to encode document context for document-level causal prediction. From the application study, we observed that on components are helpful for our proposed model. Eliminate any component degrade the performance significantly. Using both dense and sparse graph in accompany with the regularization is necessary to achieve competitive performance. Finally, in our cross-topic transferring evaluation, our proposed model shows they can generalize well over different topics in all 3 transferring modes: low, medium, and high similarity. This is the end of our presentation. Thank you for listening.